So now it's going to be an introduction to continuous systems, which is another way of talking about classical field theory. So that's classical field theory. In short, we're going to call it classical field theory, and that's it. Okay? And classical field theory is the classical version of quantum field theory, of course. Quantum field theory we're not going to do, but you can already guess that the essential difference between classical field theory and quantum field theory is the same as, between classical mechanics and quantum mechanics, which is that when you have in classical field theory the Poisson bracket, the equivalent Poisson brackets in field theory, we will have to see what those are, then you quantize it by just multiplying by I and calling that the commutator, right? So the quantizing rules are going to be essentially the same. And so classical field theory is the gate to quantum field theory. And quantum field theory is fundamentally important because it's the last truth, right? Quantum field theory is the last language, the last and best language that we have to describe nature. So there is nothing beyond quantum field theory, for sure, okay? There are speculations about things like a string theory and other mathematical constructs, but so far there is no evidence that those constructs are true. So the last truth is quantum field theory, and that's the quantum version of the classical field theory we're going to start describing right now, okay? So motivation. So what's the motivation to study classical field theory? Is that we want to describe the dynamics of continuous systems. Continuous systems. And why? Because continuous systems are, continuous systems are what we call fields among friends, right? So a continuous system is what we call normally a field. And what is a field? So it's a system with an infinite, actually continuous, number of degrees of freedom. So the idea is that from the variables that we have had so far, in which we had a label, an index, okay? So this was little n normally. So let's call it little n. Okay, so from the variables that we had to describe the system that were all labeled with an index I, which was, a discrete index going from 1 to n, we want to go to something in which the index has become, the index has become a variable. So now X is continuous. Right? So before, so the time dependence is the time dependence. That's going to give me the time evolution as before. But now what used to be a discrete label, a discrete index, has to become a continuous variable. We don't call it index. We could call it a continuous index, but we don't do it. So we just call it a continuous variable. So we have to take some sort of continuous limit of this discrete system, okay? And examples in which we need objects like this are all the fields, like the electromagnetic field, the electromagnetic field, right? Call it E of X and T, the magnetic field of X and T, or if you have in 3 dimensions like this, or the Coulomb potential, right? We're going to see there is actually the Coulomb potential and the vector potential, the true variables of electromagnetism, but not only electromagnetism, right? The gravitational field also, gravitational field. Oh man, why am I always writing field this wrong? Okay, so the gravitational field. Actually, the gravitational field, when you guys do general relativity, you guys will see that is actually a tensor which depends on space and time. And this tensor coincides with the metric of the space, okay? Etc. But we can also describe, with the, some rho of X and T, the density of some material. Okay, so that's also a field. Imagine that the density of a certain material is subject to some forces or something. And so therefore it has some dynamical equations that we want to describe. So all these problems, but particularly the most important one is the electromagnetic field, is the one that we want to describe in this case, right? Yeah, gravitational field as well, but that's going to be a little harder. So for that, you guys will have to wait until you guys do general relativity. So we have to take some limit in which we go from a discrete system to a continuous system, right? So we go from discrete to continuous. Discrete system to continuous system. We want to know how to do this thing, okay? And to do this, we're going to study a concrete example that will help us understand what we have to do. Okay, so this, we're going to study the transition from a discrete to a continuous system. Okay, so, and we'll study an example, which is a simple way to put things in place, okay? This example is going to be an infinitely long elastic rod. A rod is, in Spanish, is what we call una barra, okay? So it's a rod, okay? That undergoes a small longitudinal vibrations. Okay, so we have a rod which undergoes, vibrations longitudinally. So we can think of a system of n springs, and we'll take the limit n goes to infinity. Okay, so let's write down here, you know, so it's going to be a mass M, then it's going to be a spring, another mass M, then another spring, another mass M, another spring, another mass M, and so on and so forth. It's infinite, okay? So this is our model for this infinitely long elastic rod, okay? Okay, fine. So the mass of all these particles here at the end of the springs is going to be the same for all of them. So the mass is M. So the mass is M. So this is M. Is the mass of all these points, okay? All these particles here at the end of the springs. Okay, so now here I'm going to have the position of equilibrium here. Okay, so let me just put it here. So this is the position of equilibrium. Here is this and this and this and this. So this is the position of equilibrium. Today my handwriting is a little chaotic. Position of equilibrium. All right. Okay, but now at a certain point in time, these masses, you know, will move. Okay, so maybe the mass is now here. Okay, this is the spring. The mass is now here. This is the spring. Maybe this one was extended. Now here, maybe this one was compressed, and so on and so forth. Okay, so that is the situation. Now, I'm going to call, so this is the position of equilibrium. This is the position of equilibrium, position of equilibrium, and position of equilibrium, okay? So I'm going to call this displacement, okay, Qi minus 1, this displacement Qi, because that's going to be the particle I minus 1. This is the particle I. This one here is Qi plus 1, because this is the particle I, and this is going to be the particle I plus 1, and this will be I plus 2. Okay? So the Qi's are the variables that measure the distance from equilibrium. Distance from equilibrium. For each particle I, right? For each particle I have the corresponding Qi. Okay? Then, what is the kinetic energy for this system? Okay, what is the kinetic energy for this system? Well, it's simple, right? All I need to know is the velocity of each particle. Each particle has a mass m, so that's going to be 1/2 of the mass times the velocity squared. And then I have to sum from I equals 1 up to n, if I have n of them. Okay, so this is the kinetic energy. We will see how we take the limit n goes to infinity, but so far I have n of them, and we'll see how we do this. Okay, so this is clearly the kinetic energy. Any questions about this?
No.
Okay, now the potential. And I'm going to assume that these springs are perfect, so therefore that they follow Hooke's law, okay? So that means that this is going to be 1/2 of the, I'm going to take a constant k for each one, so the constant, the spring constant, is going to be k for all of them. So this is k, this is k, and this is k. This is m, this is m, and this is m. So k is the same constant for all the springs. And then the potential, you know, is going to be different from 0 if there is some compression or some extension, right? So if, you know, one mass and the next, you know, move relative to each other with respect to the position of equilibrium, right? If they don't compress or they don't, you know, extend from the position of equilibrium, then the potential is going to be 0. So this is the potential. And here I'm going to have to sum again from 1 up to n. Okay, so that means that I have a Lagrangian. This is a non-relativistic system. So Lagrangian is T minus V. And it's as simple as that. So I have a system given by, you know, this sum over I from 1 up to n of m qi dot square minus k qi plus 1 minus qi whole thing squared. So that is my Lagrangian. And now I have to devise a reasonable, a sound way, a sensible way, a reasonable way of taking the limit n goes to infinity. I cannot just take the limit n goes to infinity, and here I'm going to have you know, an infinite sum, and I don't know what to do. I want to take a limit n goes to infinity so that this thing, you know, goes over to an elastic rod, so that this thing resembles an elastic rod, so that this thing in the limit n goes to infinity becomes an elastic rod. Okay, and for that, of course, I have to take the limit n goes to infinity, but make sure that this thing is not discrete, right? So that I don't have, you know, one particle, another particle, another particle, another particle, but these particles have to become closer and closer together, right? Closer and closer together. So that means that there has to be another parameter, which I'm going to call A, which is the distance between these two particles when they were in equilibrium. And I'm going to take the limit when n goes to infinity and a goes to 0. This is the thing I want to do. I want to have many, many of these particles, but they have to be closer and closer together so that in the end, if this limit, you know, exists and I can make it in a sensible way, becomes a rod, becomes really, you know, some continuous system. Okay, so let's do this thing. Now the whole problem is how to take this limit and so that this discrete system becomes continuous. Any questions so far?
Fine, everything fine.
Okay, so we already see that n and a will have to be linked to one another, right? So I cannot take n goes to infinity fixing a constant, but a has to go to 0 when n goes to infinity in a coordinated way, because for instance, n times a, this is fixed, right? What is this?
The longitude of the rope.
Exactly. This is L, the length, and this has to be fixed. And another thing has to happen. M times A, sorry. M times N, this also has to be fixed. What is this thing?
The total mass of the rock.
Exactly. So this is the mass of the rod. So this also has to be fixed. Okay? Okay, fine. So then let's just start putting A's. Let's just start putting A's here so that I can, control this limit. Okay, so the limit, again, the limit when A goes to 0, n goes to infinity of m times n divided by A times n. This is, of course, the limit when A goes to 0 and n goes to infinity of the total mass of the rod divided by the total length of the rod. Okay, so this is what I'm going to call mu, which is the mass per unit length. And this is fixed, right? This is fixed. So we already see that, the natural parameter in this system is going to be not the mass of one particle, not the distance between one particle and the next, but the mass per unit length, for instance, okay? And of course, this is the same as the limit when A goes to 0 and n goes to infinity of, I can cancel the ends, of m divided by A. So this is also mu. Okay, this is also mu. Good. So let's go back. We have our Lagrangian, and we're going to start putting here A's and N's so that I can take the limit, fixing mu to be a constant. So our Lagrangian was 1/2 of the sum from I equals 1 up to n of m qi dot square minus 1/2 the sum from I equals 1 up to n of k times qi plus 1 minus qi squared. Okay, that's exactly what I had, right? Yes. Good. So we start by, putting A's and N's in the right place. So that means let me divide this thing by A. Let me divide this thing by A and multiply this whole thing by A. That way I already have m over A. And I know that this is going to have a very easy limit because this is nothing but mu. Okay? All right? And then I have an A in front of the whole thing. So this A in front of the whole thing, I'm going to define it as, for reasons that will become clear later on, I'm going to write it as sum from I equals 1 up to n of A, that very same A, times something I will call Li. And Li is the rest, of course. Okay. Equations of motion. Given a Lagrangian, it's immediate, how to write down the equations of motion. d dt partial of L with respect to q dot I minus partial of L with respect to qi equals 0. Okay? So let's compute that. So that means that 0, which is this 0 here, has to be partial of L with respect to q dot I. If I take the derivative of this thing with respect to q dot I, that's the only term I have to look at. Okay? So that means that I have m q dot I, and then derivative with respect to time, so that's q double dot. You agree? Okay?
Yes.
Now, let us do now the same thing, the dependence of L on Q. And this is a little less obvious than one would think, because when I take the derivative of L with respect to Qi, I have to remember that there are two dependencies on Qi, right? There is the piece that goes like 1/2 of K over A, Qi plus, oh man. qi plus 1 minus qi squared. So here there is a qi, but there is also the next term, k over a, qi minus 1 squared. And here there is also qi. So I have to take into account the two dependencies on qi, here and here. In this sum, there are two terms for each qi, and the two terms contribute to this derivative. Okay, so let's compute this thing. And this is k qi plus 1 minus qi, so that's one of them. And the other one comes with a plus sign, qi minus 1. So that's the equations of motion for each I from 1 up to n, all the q's that I have. Now, I cannot take the limit a goes to 0 here because I have to fix all these parameters. So that means that I'm going to divide the whole equation by a. So I divide by a, I divide by a, and I divide by a. Okay? And now I'm going to take here and divide by a again. So that's a square, and multiply by a here, a squared, and multiply by a here. So that's the equation I'm going to look at. Okay? Now, this is mu. So that I don't have to worry about. Okay? So this is already something that is going to be fixed. Now, I'm also going to take fix k times a. So this is also going to be fixed. So the limit when a goes to 0, n goes to infinity of ka, this is also going to be fixed. I'm going to call it y, and this y has a name. It's called Young's modulus, and is also fixed. Young's modulus is something that tells you how elastic a rod is. Okay, so that's going to be y, and this is also going to be y. And now I have to look at what happens to these quantities, q double dot I, qi plus 1 minus qi over a squared, and blah, 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 when I take a goes to 0. And so this is the thing that I'm going to do now. So I take qi, and I want this qi when a goes to 0, n goes to infinity, to be replaced by q of x, right? The index I, discrete, has to become a continuous index x. Okay, so then what is qi plus 1 minus qi divided by a? If I take this limit, what is the thing that is going to correspond that? So in other words, what is the thing whose discrete version becomes this? What do you guys think?
The derivative with respect to x.
Exactly, the derivative of q with respect to x, function of x. Okay? Well, if I do this, then let's go back to the equations that we had. So here they are. So I'm going to write them again. So that's going to be m over a qi double dot minus ka qi plus 1 minus qi divided by a squared plus ka qi minus qi minus 1 divided by a squared. This is 0, right? So let's take the limit when a goes to 0 of this thing. So limit, let me do it like this. A goes to 0, n goes to infinity. So this goes to mu times the second derivative of q with respect to time. Here there is no issue, right? This is going to be a function of x and t. So here there is nothing, right? There's no The discrete version is obvious. Just x gets replaced by I, and that's it. Okay? Now, how about here? Well, minus Ka is minus y. This is Young's modulus, as we were talking about. Okay? Young's modulus. Let me pull an A. Let me put this A here momentarily. So that's going to be Young's modulus divided by A. And this is what? This is the derivative of Q with respect to X. But this is at the point X. And this is what? This is minus the same derivative of Q with respect to X, but this is at the point X minus A, right? And this is 0. This is when A goes to 0, N goes to infinity. A goes to 0, A goes to 0, N goes to infinity, right? So this factor goes to this factor, and this factor goes to this factor. Okay? So what do we have? Well, the first term is mu, the second derivative respect to time of Q of X and T, minus y, and now we have the derivative of Q at the point X minus the derivative of Q of the point X minus A divided by A when A goes to 0. So this goes to the second derivative of Q with respect to X. And this has to be 0. Okay? So we have already obtained a continuous version of this discrete equation of motion, right? So this is the equation that we obtain when we take this limit. This is the equation of motion for an elastic rod. And indeed, this is the equation of motion for an elastic rod. Okay, and for instance, the velocity of propagation on this rod is nothing but the square root of Young's modulus divided by the density of mass. Okay, so once you're given, this is a wave equation, right? This is clearly a wave equation. This is a wave equation, as you guys have seen in many other examples. And so the velocity of this of the waves in the system is given, by the ratio of these two coefficients of square root. So we have already taken the continuous limit, at the level of the equations, but we also want to take the continuous limit at the level of the Lagrangian. And once we have the continuous limit at the level of the Lagrangian, and we have the continuous limit at the level of the equations, we are going to be able to derive, Euler's equations that take you from the Lagrangian to these equations of motion, right? So let's do that. So what was the Lagrangian? Well, remember, the Lagrangian L was the sum over I from 1 up to n of A times Li. And this was the sum over I from 1 up to n of A times Li. And Li was what? It was 1/2 of the mass over A, Q dot I squared, minus Ka times Qi plus 1 minus Qi divided by A, whole thing squared. Okay? But now we know that this goes to mu, this goes to Young's modulus when a goes to 0, n goes to infinity. So the Lagrangian becomes, if I take a goes to 0 and I have a sum of all these things, what do you guys think that this becomes to? Right? This now will have a clear expression. It will be 1/2 of mu derivative of q with respect to t, function of x and t, squared, minus 1/2 of the Young modulus, and this is the derivative of q with respect to x, of x and t, squared. So we know that this term here, the summand, becomes in this limit this function, derivatives of q with respect to x and with respect to t. I have to sum over a from 1 to infinity this thing. So this whole thing, not just the summand, but the whole thing, where does it go when I take a goes to 0, n goes to infinity? A goes to 0, n goes to infinity.
The definition of Riemann's integral.
Absolutely. Very good. Yes. So this is the integral over x of this whole thing. From 0 to L, where L is the longitudinal, the longitude of the length of the rod. Huh? So I wanted, where did I define the length? I'm going to call it little l, so that you guys don't confuse it with the Lagrangian. So now we have a Lagrangian. Now I have a Lagrangian, and now I have the equations of motion that I have to derive from this Lagrangian. Remember, the equations of motion were mu d squared q. And actually, at this level, since now q depends on x and t, q depends on x and t, I mean, the normal notation is not to talk about full derivatives, but partial derivatives, right? So that's what I'm going to do now. So I'm going to just change notation here. And I'm going to write here the second derivative of q with respect to t is a function of x and t. So this is a 2. Oh, man, 2. Minus Young's modulus, second derivative of q with respect to x, of x and t. And the same thing here. Here, now that I recognize that this is a function of x and t, I just, write partial derivatives. Okay? So now, and this equals 0. So now I have to devise, which are the equations that, lead from here to here. Euler Lagrange equations, which are the equations that, relate this Lagrangian and these equations of motion. And this is something that we will do the next day, because I think that the class is over, right? So it's 2 to 3, 3 to 4. Yeah. So I should finish right now. So anyway, so we'll connect the Lagrangian and the equations of motion, the next day. Any questions?
Okay.
I'm assuming that you guys have already done exercises of canonical transformations with Javier, right?
Yes.
Okay, so then that is included. So it's included, the limit of what is included in the exam is fixed by the exercises that you have done with Javier.
Okay.
All right?
Okay. Fine.
Okay, so that is all then. Okay,
Okay.
thank you very much.